So today, through this video lecture, we are going to see how can we calculate strain energies for different determinate structures or basically determinate beams under different loading condition. So we are going to see a step-by-step procedure. So in later stages or in the advanced stages, you can actually skip many steps. So let's see the basic structure. So we are going to start with the very basic structure, that is cantilever beam. Okay, when we consider, this is the case one what we are handling, a cantilever beam subjected to a point load at the free end. So let the parameters be physical parameters: length L, modulus of elasticity E, and moment of inertia I. So I think we have discussed this in the previous lecture, but still let's see how this can be solved. So what we used to do is we'll be dividing it into segments. So if you are representing this particular beam as reactions, what we are going to find is something like this fixed end. So we are going to have vertical, horizontal, and maybe a moment. Okay, 3 reactions may be there, and here we have the external load as given in the problem. And we know that the beams are divided into segments depending upon the location of point loads. So here this is one point load location, this is another point load location, so you just need to have one segment, and that segment is having the properties L and EI. Okay, now if you want to calculate strain energy, we basically need to have the values in a table format, and that also we discussed. That is, the table should be having segments, flexural rigidity or EI value, limit, origin, and the moment value. Okay, so here we just have one segment, so just segment 1 is enough, and the EI is constant within the segment, so I'm writing it as EI. The limit is, the total length of the beam is L, so the limit is from 0 to L. For cantilever beam, it's always advisable to take the free end as the origin. So I'm considering, say we need some names, say I'm naming this point as A and this point as B. Okay, if that's the naming, then the origin, I'm considering the free end B, and I need to take the moment. So to take the moment, I need to consider the section in between or within the segment. So within the segment, I'm considering a section, say XX, and the distance from the origin will be marked as X. That you should be very careful. Always mark the distance X from the origin. Here the origin is B, so the distance, this distance is X. And we will be calculating the moment values. So for calculating the bending moment, if we want bending moment at this section, we will fix this point. Okay, and in the last video we were doing the same thing, so it's like fixed at this point, and I have a point load, right? So I'm applying a point load in the end, and it's getting bent in the shape which is hogging. Okay, which means the value is negative. And what is the magnitude? If I'm taking here, W is the load, X is the lever arm, so Wx is the moment, and as it is a hogging moment, the value is minus Wx. Now I can simply do the integration part to get strain energy. We know that the expression is m square dx by 2EI. So we'll be substituting the different values, and we can see here u equal to integral, the limit is from 0 to L, that's the limit, and m is minus Wx. So minus Wx whole square dx by 2EI, which is going to give us here this minus Wx whole square becomes W square x square. I'm taking the constants out, so W square I'm taking out, 2EI I'm taking out, so what remains is an integral 0 to L x square dx. Okay, x square dsx x cubed by 3, integral x square dx is x cubed by 3. So w square by 2 EI x cube by 3 0 to L, which is going to give me the answer as w square L cube by 6 EI. Okay, so that's the strain energy for a cantilever beam subjected to a point load at the free end. So that's the first case. Now we are dealing with the second case. So in the second case, instead of the point load as a load like this, I'm applying a moment. A moment I'm applying at the free end. Again, I'm keeping the parameters as L, E and EI. And if I'm converting the beam, what I'm going to have reactions here, and I'm having moment here, M, okay, L, E, I. One point load location, second point load location, I'll be getting a single segment 1. Again, I'm going with the table S, E, L, O, M. Okay. So there is just one segment, and the modulus of elasticity is constant and the value is EI. Limit is 0 to L, and the origin, this is also a cantilever beam, so I'm considering the origin, again the origin as the free end, so I'm considering B as the origin, and I'm taking the moment. The section is XX at a distance of X from the origin. The origin is B, so this is X. So if I consider the moment here, okay, the magnitude will be, if I'm looking to the right, the magnitude is M. Now I need to check whether it is sagging or hogging. So I fixed at this point. Now I'm applying a moment like this. So I'm applying the moment and it is bending in the hogging direction. So this value is basically negative. Now I can use the strain energy equation, that is integral m square dx by 2 EI. So integral minus m whole square dx by 2 EI, and the limit is 0 to L. So minus m whole square becomes m square, which is constant. So m square by 2 EI. Then what left is 0 to L. Integral dx is x within the limit 0 to L, so it becomes L, and I'm going to get the answer as m square L by 2 EI. So that's the answer for the second case, the strain energy for a cantilever beam subjected to a moment at the free end, and the direction of the moment is clockwise. What happens if this moment was in the anti-clockwise direction? Will there be any change for the strain energy value? Okay, if this was anti-clockwise, what would have been the difference? The difference would be this m will, minus m will become plus m, right? So I'm considering the third case within this one itself. If the moment was something like this, okay, this m, instead of this, if it was something like this, then what happens? Then I can see here it is in this direction, okay, like this. So when I apply it, it's sagging. Sagging is positive, so this minus m becomes plus m. So here also it becomes plus m whole square. Will there be any change for the value? No, the value remains same. Okay, so whether it is clockwise or anti-clockwise, I'm going to get the same value for strain energy. And you should know that the strain energy is always a positive value, right? Because we are squaring the moment, we are going to have it as a positive value. Now we are going to see the next case. Okay, we have seen two cases. We'll move through these different cases quickly, and if you have any doubts, you can slow down the video or you can just pause it and can go through the different steps. So we are going to the third case. Okay, we are going to the third case. What we have here is a cantilever beam subjected to a UDL over the entire span. Okay, the physical parameters LEI. Okay, so let's see how to solve this. So the first step, convert it into a beam with forces. Okay, so what I have here is a system like this. So this is the location of point load, and this is the only joint what we have. So there is just one segment. Okay, there are no other point loads, so just one segment. Now I'm going to write the table. So SE LOM. So just one segment, hence it is 1. Then the Young's modulus is constant, so EI. Limit is 0 to L. Cantilever beam, so the origin will be at the free end. Again, I'm naming it as A and B. So the origin is B. I need to take the section. I'm taking the section within the segment, and from the origin the distance will be X. Now I'm considering the moment here. Okay, so what is the moment here? If I'm looking to the right, this is having a magnitude W, right? So what is the total load on the right hand side of this section? The total load is W into X. This is W per unit length, right? So W into X is the total load, and this WX will be acting at the centroid. Okay, centroid will be at a distance of X by 2. So what you are going to have the magnitude as WX is the load and the lever arm is X by 2. Okay, WX is the load and the lever arm is X by 2. Okay, lever arm of the load or the net load will be acting at this point, which is the CG of the load. So it is at a distance of X by 2. So WX into X by 2. So that's the magnitude. Now we need to think about the direction. So if I have a system like this, and if I'm applying a force, okay, if I'm applying a UDL, so it's not a concentrated force, a distributed force. If I'm applying, it's going to bend in the shape of hogging, which means it is negative. So I'm going to have the value as negative. Now I'm going to use the condition integral m square dx by 2 EI. I'm doing it here. So u equal to integral, the limit is 0 to L, just one segment, and the m value is minus wx square by 2, minus wx square by 2 whole square dx by 2 EI. Okay, so I can take the constant terms outside. So square of minus become positive. So w square by 4. Okay, w square by 4 is the constant that is coming from the numerator, and 2 comes from the denominator. So it becomes w square by 4 into 2, that is 8 EI. Okay, that is a constant part coming out from it. And 0 to L, x square square, that is x raised to 4 dx. So this will become w square by 8 EI into x raised to 5 by 5 within the limit 0 to L, which means L raised to 5 by 5. That is w square L raised to 5 by 40 EI. That's the strain energy. Okay, so whatever the load may be, all you need to do is to get this table properly, to get the moment value properly, to get the segments properly. Once you have this, then it's the integration part. And when the problem is having magnitude, there is a very easy way, because integrals that is having a limit can be integrated using the calculator itself. Okay, so it's going to be very easy for you. Once the values are variables, you may have to do this manual part, or else you can directly go with the calculator for doing integrals with limit. Now we're going for the fourth case. So here we are having a bit different. So let a point load be acting at this point, say having magnitude P. This is L by 2, this is L by 2, and everything is having constant EI value. So the steps are same. So first convert it into forces like this. Okay, L by 2, L by 2. Now here the location of point load is one is this, and we have a point here, right? So we need to have two segments. Okay, segment 1 and segment 2. Earlier we were having just one segment, here we have two segments. Now let's plot the table. So SELOM. So I'm talking about segment 1. So to get the fill the details that's available. EI is constant in that segment. The limit is 0 to L by 2, right? Because it is having only length 0 to L by 2. So here we need to be very careful about the limit and selection of origin. Okay, so there's no hard and fast rule for selecting the origin, but there are some good practices or some easier approaches for selecting the origin. So we are going to take a section in the segment 1. Now just look to the left and look to the right and start observing. So when you're looking to the left, if you want to take moment, you need to first solve the values for these different forces and then you need to take the moment. Okay, but if you are looking to the right, okay, what is the advantage? There is just one point load, so it is easier to calculate the moment if you are looking to the right. Okay, so we want the origin to be from the right, and if you are considering this particular point, okay, we name something A, say B and C. If I'm considering B as the origin, okay, I'm considering B as the origin, so what will be the limit? The limit will be 0 to L by 2. If I'm considering C as the origin, okay, I can consider any point as the origin. It is the choice of the users. If I'm considering C as the origin, okay, if C is the origin, the range or the limit of segment 1 is L by 2 to L, okay, because this distance is L by 2 and this distance is L. So depending upon what the origin we are choosing, the limit will change. Okay, I will show that. So in this problem itself we will discuss. So if I'm considering, for the first case, I'm considering the point B as the origin for segment 1. So the segment 1 is B is the origin, so 0 to L by 2, right? Parallelly, I'm making this calculation for you. So SCLOM, okay, segment 1 itself, EI, and I'm considering the C as origin. If C is the origin, the limit will be L by 2 to L. Okay, we need to be very careful on selecting the limit and the origin. So depending upon the origin, the limit will change. If the origin is B, this is the limit, because the value ranges from 0 is the origin point up to L by 2, that is segment 1. If C is the limit, the origin will be L by 2 to L, right? So we need to be very careful. Now if I'm considering this case, okay, that's the case 1 what I'm selecting. So if B is the origin, the X will be the distance from origin, which is this, okay. But if I'm taking C as the origin, what will happen to X? X will be this distance. I'm calling it as X1 and I'm calling it as X2. Understood? So depending upon the origin, the X changes, right? So if I'm considering this, so this is X. So what will be the moment here? If I'm taking the moment at this particular cross section, I'm looking to the right, so the moment will be P into X1. Okay, if I'm considering B as origin, it is P into X1 or PX. Okay, now I need to get the sign. For the sign, I'm holding it here. The load is getting applied here, okay, in the center. The shape is hogging, hence it is minus. But if I'm considering C as the origin, now what happens? The length what I need to consider, so this distance is my X, okay. So what is this distance? Because if I want to calculate the moment, the force is P, the lever arm is this small distance, and what I have X as this distance. So in here, the moment will be P into X minus L by 2, okay, because X is this total distance. What I want is only the small distance, right? The small distance. So X minus L by 2 will give me the small distance. So depending upon the origin what we are considering, the limit and the expression for bending moment will change. Okay, so whatever the easier option is, choose that one. Now you can see here, if you are going for integration, seeing these two expressions, I will definitely prefer this one because this is comparatively easy to integrate. This one looks a bit more time consuming. Okay, so accordingly you can choose the right one. Now we are going for segment 2. Okay, segment 2 is this. Now in segment 2, the EI is constant. The limit and the origin I need to decide. So the free end is available, so I'm considering that as the origin. Now the range will be, if I'm considering this as the origin, segment 2 is from 0 to L by 2. Okay, if C is the origin, 0 to L by 2. And what will be the moment? So if I'm taking a section here in the segment 2 and I'm looking to the right, what is the bending moment? It is 0 because there is no load in the right side, hence the bending moment value is 0. Okay, so here also you can have the same. Okay, so EI is constant, range is 0 to L by 2. I'm keeping the origin as C, the value is 0. And I can just do the integration because I have the two segments. I have the expressions for bending moment, origin, limit, everything is available. Now let's try to solve it. So I'm going to calculate the strain energy value, that is U. So what will be the strain energy value? Integral m squared dx by 2EI. So here we have two segments, hence this will be first segment, that is the range 0 to L by 2. I'm doing with this 0 to L by 2. The expression for moment is minus px whole square dx by 2EI plus the second segment. The limit is 0 to L by 2. The expression for moment is 0 square. So 0, so m square becomes 0 square dx by 2EI. And once I do this integration, I'll be getting the final result. So this is multiplication with 0, so I can directly consider this value as 0. Now I have this part. So minus px whole square becomes p square x square. So I'm taking the constants outside. So p square 2EI is outside. And integral 0 to L by 2 x square dx, which will give me the answer as p square by 2EI into integral x square dx is x cube by 3. Okay, I need to substitute this. So it becomes L cube by 8 by 3. Okay, so it will be p square L cube. So now it becomes 8 into 3, that is 24, 24 into 2, 48 EI, which is the strain energy for this particular problem. Okay, even though I discussed two alternate approaches, there is no need for you to go for these two approaches. You can just go in one approach. Even if you do this integration also, you are going to get the same result. So you need to take the easier option. To get the easier option or to identify the easier option, the only thing is that you need to practice. If you keep practicing few problems, you will know which is the easier option. Okay, so this video will wind up at this particular point, and in the next video we will deal with the cases of simply supported beam. So now we were dealing with cantilever beams, that is the easiest option. Now we will go to the second type of problems, that is the problems involved with simply supported beams. Okay, thank you.